maybe doing some exercises, but of course, time is short after Christmas. So please work on the topics now. Well, we were discussing pH. You remember pH, acidity, alkalis, and all these topics. And here, very brief, we had this discussion. What is the pH when we have a solution of a strong or a weak acid or base in any aqueous solution? And here the example for a strong acid is similar to a strong alkali. Then we just can take the the concentration of the acid, because when we have a strong acid, the equilibrium is totally on the right. That means the initial concentration of the acid is, when we have it 1:1, the same as we have it here for the protons. So we can say when we have a strong acid, the pH is directly related to the concentration of the acid, because this is similar to the concentration of the H3O plus, or the protons, and the negative log of the protons is the pH. Here we discuss the pKa, that pKa level or the Ka level. If Ka is big, it is a strong acid. And we have the negative log of Ka, which is pKa. So a small pKa means a strong acid. So the pKa value defines the acidity. The pKb value defines the alkality of an alkali. -8 is a very low number. So here a small number means a strong acid. +4 is quite big compared to -8. It's a weak acid. In this example, the acetic acid. This is about that. And here for the example of the acetic acid, we discussed that here this proton is the one which is delivered to form the H3O plus, and we have these acetic anion or small H adds acetic anion. And here the equilibrium is not totally on the right, it's more on the left. So it's a weak acid. Using the same formality, Ka is the product of the concentration of the products, H- and HCO plus, over the initial concentration of the acid. Water we don't have to take into consideration because it's a fixed number. The solvent is water, so a lot of more molecules. We had the number 55.5 mole per liter. Then the Ka is depending on the product on that over this. Here, for example, acetic acid is 1.8 times 10 to the power of -5 mole per liter. And this, if you calculate out of this the pKa, maybe you use your calculator. The pKa is the negative log of this number, 1.8 times 10 to the power of -5. And this is 4.74. That's the number we had over here. If you remember, that's the acetic acid. You can check it via calculation. It must be this number. When we have this equation here, the equation 2, then we could say, even in the case of a weak acid, related to this equation, when there is a reaction to the right side, we have a ratio 1:1. That's why we can say H3O plus is similar to the H minus concentration. And when we integrate that into this, we have H3O plus square over the HATS concentration, or the H3O plus concentration is the root of Ka times the concentration of HATS. Well, we are looking for the initial concentration and the current concentration, because when it is a weak acid, we cannot say that the concentration of the acid is the same as the H minus or the H3O plus, because here only partially it reacted to the right way. In a strong acid, it's totally here. So we can say this is similar to that. But we have a weak acid, so quite a lot is here. Only partially we build that. So the current concentration in the solution is that what we have when we added it. It is depending on the start concentration, which we had at the beginning, minus those which are reacted to the H minus. Partially, a few of them are reacted, but not too many. This is what we wrote here. So the H3O plus concentration, that is what we had already here, is the root of Ka times the concentration of HATS. In a weak acid, Ka is very low. So the concentration of these H3O plus is very low compared to the initial concentration of the HATS. But if not of them are really reacted, we can even say maybe it is the concentration, the current one, because not so many reacted. And that is what we used then to go further. That is what we had already. The pH is the negative log of this. And when we transform it, we come over that the pH is pKa minus the log of HATS over 2 for weak acids. So for weak acid, it's a little bit more difficult to calculate the pH. We need this formula. For strong acid, we can say it's the concentration of the acid. And then it's similar for the H plus. And then we have it for weak, no. For an example again, acetic acid, the pKa is this number. We have a concentration of the acid of 10 to the power of minus 2 mole per liter. When we integrate the numbers here, we came over that the pH level is 3.37. In a hydrochloric acid, the concentration of the 10 to the power of minus 2 will lead to a pH of 2. It is 1.4 nearly difference, but it's a logarithmic scale. That means one shift in this logarithmic scale means 10 times more or less. So that's quite a lot. So in general, for the weak acid, that is what we ended up last week. Okay? Fine. Now, let's go on today's lecture. Well, it's Nicholas. Well, we'd like to go on with that. Now, using the example of an alkali, yeah? It is the same strategy. We already know it. We have now an alkali, A minus, plus water. And we have an alkali which is accepting a proton, and OH minus is built. This is a base or an alkali. So alkalis are accepting protons. Acids are delivering protons. So here the A minus accepts a proton from the water, The water acts as an acid in this example. This acts as a base. When we read it from the right to the left, now this is the acid and this is the base, because this accepts the proton and this delivers the proton to the water, to the OH minus, to the hydroxide anion. So in this example, the Kb, when we use our formula, the Kb is the concentration of the AHA times the concentration of OH minus over the concentration of the alkali water. Again, we don't have to calculate it. The pKb, of course, is the same, negative log of the Kb. So in general, we have those two examples. One is the acid, HA plus water. And we have here A minus plus H3O plus. The Ka level is concentration of A minus times H3O plus concentration over the concentration of the acid. This is 1. And the Kb is this one here. Now, when we see, okay, here, this is the acid, here, this is the base. We just do it, Ka times Kb. What will happen when we multiply those two? Then we have Ka is A minus concentration times H3O plus over the concentration of the acid. And the Kb, we can multiply. Again, it is HA now. Here, we look up here. HA times the concentration of the hydroxide anions over A minus concentration. When we do that, we see we can cancel the A minus, we can cancel the HA, because we have the same up and down of our term. And that means now Ka times Kb is the concentration of H3O plus times the concentration of OH minus. And what is that? Do you remember what's that? The concentration of the protons times the concentration of the hydroxide anions. We already had it in some hours before. It's Kw, yeah, it's the ionic product of the water. Very good. So this is Kw. And do you even know the value? Yeah, it is 10 to the power of negative 14 moles square over liter square. That's the ion product of water. Well, what does it mean? That means now, of course, we have one system. We have a system where HA reacts as an acid and the A minus acts as an alkali. And when we read it from the left to the right or from the right to the left, we can multiply Ka times Kb. And then in this case, it always leads to the ion product of water. Or if we know one of that, if we know Kb, for example, we can say this is Kw over Ka. Huh? So automatically we know the other one. Or we can even say pKa plus pKb. What is that? It's 14. Huh? This is true when we look to one system which acts as an acid in the one way or a base in the vice versa way. It's always true. So for a corresponding acid-base pair, this is true. There's a question in the chat, sir, when is the mock exam? I already mentioned that several times. There is no mock exam. You have the chance to do some exercises in the tutorial Monday with Joseph Erl. And there will be some exercises. And we will do some exercises after Christmas, but you should do them. I will put them into the iLearn, and then we can answer questions if there are some problems, if there is anything to be discussed. But there will be no mock exam. Just exercises with questions which could be even asked in an exam, of course, but you should work on them and then we talk about it, but it's not a typical mock exam. It's exercises, I call it exercises. You won't be here for a mock exam and writing and then I collect the paper. You have to do it at home and then we discuss problems, or we can even go through the solution or the results of these questions. No mock exam. Would you please show the first page of the page again, the first part of the page again? Hopefully it works. Okay. Well, we have some examples. For example, when we build the salt, always when we have an acid and an alkali reacting. For example, we have the acetic acid and we add hydrochloric acid, or not hydrochloric acid. We add an alkali, a sodium hydroxide. What is created? We have acetic acid and sodium hydroxide. Can you imagine what will be created? Well, the acetic acid, you know, CH3COOH, sodium acetate, yes. And the sodium hydroxide, then when this reacts, the CH3COONA, minus here plus, is built as a salt plus water. So when we have the reaction of an acid with an alkali, we build the salt and water. That's a general rule. This is the salt and water. And this is the acid, and that's the alkali. So putting an alkali and an acid together creates salt and water. In this case, what are you expecting will be the pH when I have the same concentration of acid and alkali and put them 1 to 1? Yeah, this is a strong alkali, that's a weak acid. So the overall reaction will have more alkali, it will be alkaline. A strong acid and a strong alkali, it will react to neutrality. A weak acid and a weak alkali to neutrality. Strong acid, weak alkali, acidic, and strong alkali, weak acid, alkaline. But in general, we do that when we have a wastewater before we put it into the sink. And we know there's nothing else, only an acid in, we can neutralize it with an alkali. We put alkali to it, we measure the pH level until we have 7, then it's neutralized, then we created water, no problem for the sink, and a salt. Most of the salts are no problem for the sink as well. Huh? So we can put it into the wastewater after neutralization. Why is it important to think about neutralization before we put the acid into the sink? Very good. Yeah, it will corrode. Even the alkali is not very good. It always enhances the corrosion. So it's a good idea to neutralize before putting it into the sink. Okay. Then let's go on. So now we are solving sodium acetate in water. This is sodium acetate. When we do that, let's do it. Sodium acetate is, of course, CH3, COO minus plus Na plus ions, and we have them in water. And then we always write it as a balance. Now, this acts as it's a quite strong alkali because it's a weak acid. The acetic acid is a weak acid, meaning the corresponding anion is a relatively strong base. You can follow? If we have this one, that's the acid, and this is weak. Automatically, the corresponding anion means now it's more strong than the weak acid. So this leads to, not very strong, but more strong alkali. Relative strong, let's say it like this, alkali. So this acts as an alkali. What happens? It takes the proton from the water. Then we have the acid here. We have the Na plus ions, and it took a proton. So we have OH minus. When we now look to this reaction and write down the Kb, because this is an alkali, the base, we have to calculate the concentration of the acid, CH3COOH, times the concentration of the OH minus. Of course, we don't have to calculate the sodium ions. We have them on the right we have them on the left, and they are not interfering the pH. So we don't need them for the Kb. But we need the concentration of the acetic anion. The water, again, not to be considered because it's a fixed number. When it is reacting, we have a 1-to-1 situation again of the acid and the OH minus. So the concentration of the acetic acid must be the same as the OH minus because it is built 1-to-1. So the Kb can be written as this is same, the OH minus square over the acetic anion concentration. Or even here, the OH minus is the root of Kb, or Kb times the concentration of the anion. When you look to this equation here, let's call it equation 1. Then when it is reacting, we have a 1-to-1 ratio. If you look to the reaction, we have built one acid molecule and one hydroxide molecule. When it is reacting, we build one of this and one of this. So we can say it's a 1-to-1. So the concentration must be the same. That or that is the same. So 1-to-1 ratio is what we had already several times. Look to the chemical equation when it is balanced. And then you see it is 1-to-1. It is different. It could be even two of them, then it's 1-to-2. But here 1-to-1. Here, no, because we have an initial concentration which we put in, and we don't know up to now how many of them reacted to the right side. But when they did, those are the same concentration. No, because a part of it reacted. And for those who are reacted, then we have a 1-to-1 relation for those, but only for those who reacted. And there are remaining a few of them, but the concentration then is this one minus the concentration of one of them. Because here we have again a 1-to-1, but here we have initial concentration and then the concentration in the solution after it reacted. And this one is the initial minus this or minus that. Because here we have a 1-to-1. Did you get it? Yes. All of you? No, because here we don't know how many reacted. If we are very strong alkali, we know all of them are here. Then we don't take them as, we can say the initial concentration we put in, totally reacted. And then we say, okay, then must it be the same value we had here for the concentration. But if this is not strong, we don't know. Only a part of them reacted. Remaining a few of them or more That is what we don't know, how many are remaining. But what we know is when they reacted, on the right side, it's a 1-to-1 ratio. This is what you should train a little bit, how to read a chemical equation, huh? Because that is what we really need, even in the exam. You must understand, first of all, of course, balance the equation. That's clear. We have 1C, we have 1C, we have 3, 5H, we have 3, 1, 2, 5H, we have 2O, we have 2O, we have 1 sodium, we have 1 sodium. So everything's fine. It's balanced. And then what we are not knowing is it on the right? Is it on the left? Where is the balance? And if this is not clear that it is a strong alkali or a strong base, it's not totally on the right. So then we have this complicated formula to calculate the pH or even the Kb, all these things, because we don't know exactly. But what we can say, we have a 1-to-1 ratio here. And when we take that, this is the consequence. Now, when we have a look to equation 1, the salt, the initial salt, is completely solved. This is completely solved. When we put sodium acetate into water, it's totally solved. We are below the solubility product. Remember, the solubility product is a number which helps us to decide, can we solve these amount of molecules in 1 liter of water or not? We are now in a situation that we say, okay, we are below, we can solve that amount what we are looking to. Everything is solved. What does it mean? We don't have the solid particles. At the beginning, we have particles, crystals of sodium acetate, and we put it in water, and then they are solved. We can't see them. It's a solution. And we are below the solubility product, so everything is solved. So we have the ions, solved ions in there. That is this thing. That means now, when this is the case, the concentration of the CH3COO minus, it's totally solved. That means it is the initial concentration of the salt we put in. This is the initial concentration, but because we say everything we put in is solved, so we have the same concentration again. How to interpret these balances? And this is what we call the concentration of the base. That's CB, concentration of base. And now coming back to the formula above, Kb is the, we had it already, it's OH squared over the concentration of the acetic anion, means the OH minus concentration is the root out of Kb times, and that CH3COO minus, we call it Cb. which is similar to, say, it's KB to the power of 1/2 times CB to the power of 1/2. And the POH, now the negative logarithm of all of that. So the negative logarithm first of the OH minus concentration. And this is, looking to this formula, we can transfer it mathematically. It is PKB minus the log to the power of 10 of CB over 2. So we can say this is PKB minus the log to the power to the base 10 of the concentration of the salt, because this is the concentration of the salt. And that's similar to CB over 2. And as already mentioned, when we have the pKa level of this acetic acid, we remember which is 4.74, automatically the pKb of that anion is 14 minus 4.74, which is similar to 9.26. So the pKb level is clear. Now pKb, we know it. We have the pKb here. And now let's do an example for the initial concentration of the salt, of sodium acetate. We say the initial concentration of the salt CH3COO sodium acetate. The sea salt is 0.1 mole per liter, which is similar to 10 to the power of minus 1 mole over liter. Now we can integrate this into the formula. The POH is PKB minus the concentration, minus the log of the concentration, which is 10 to the power of minus 1 over 2. And this is the PKB, we had it, is 9.26. 9.26. So the negative log to the 10 of minus up minus 1, what is it? At the end, it is plus, it's plus 1. And so here we have a plus, sorry, it's a plus 1. And then we have plus 1 over 2, which is 10.26 half, which is 5.13. when the pH, pOH is 5.13, automatically the pH is 14 minus 5.13, and this is 8.87. So what did we find? We had a salt of a weak acid and a strong base. This sodium acetate, this is a salt of a weak acid, which is CH3COOH, and a strong base, which is sodium hydroxide. The pH level, pH is above 7. And this is alkaline. So if we have a salt out of a weak acid and a strong base, it is solved, but at the end, it reacts alkaline. So in general, salts of first a weak acid and strong base always leads to a pH level above 7. No, here we had nearly 9. A strong acid and a weak base. What do you think is the pH of a strong acid and a weak base? The level, is it below 7? Yeah, pH is below 7. And the third option, a strong acid and a strong base. What will be the pH level of this salt? pH is similar to 7. Yes, of course. So if the one which is more strong influences the pH level, but if they are nearly the same, it's nearly 7. If it is a big difference, we have much below or much above 7. If you have the same strength, it's exactly 7. HCl and sodium hydroxide, they are in the same level of strength, it's 7. Yeah. 7.0 is when we have a strong and same strength of both. If there is one more strong, of course, then it's more into the more below, or a little below 6.9 or whatever, or 7.1. you can calculate it exactly, knowing the pKb or pKa levels. Then you can calculate it exactly. When we try to neutralize, well, let's say we have at the beginning a solution which is acidic, and we try to neutralize it. What do we use for that? When we have an acidic solution and try to neutralize? Well, we need an alkali for the neutralization. And we can do that drop-wise, adding drop by drop to a solution of an acid. We know how this procedure is named? Titration. Very good. So let's do a titration. In theory, we will do that in the lab work. So let's start with HCl. At the beginning, the concentration of this HCl is 0.01 mole over liter, which is 10 to the power of -2 mole over liter. So what will be the pH at the beginning? 1. To 10 to the power of -2, negative log of -2 is 2. So the pH at the beginning is 2. And now we are titrating with a strong alkali, sodium hydroxide. And we use the same concentration of the sodium hydroxide, even 0.01 mole per liter, which is similar to 10 to the power -2 mole per liter. Now, of course, it's the second question is relevant. Beside the concentration, what is relevant when we'd like to think about how many protons or how many hydroxide ions do we have, the volume? Of course, let's say we start with HCl with that concentration, but in our beaker, we have only 10 milliliter. So at the start, 10 milliliter of HCl solution with the concentration of HCl is 10 to the power of -2 mole over liter. Now, when you have to calculate how many protons, how many mole do we have in 10 milliliter with that concentration, what do we have to calculate? So the number of moles, N, is the concentration multiplied by the volume. Now, in this example, concentration 10 to the power of -2 mole per liter. Now we have to transfer 10 milliliter into liter. How many is that? 10 over 1,000 or 10 power -2. Is that right? 20? Yeah. And that means not volume, that's liter, sorry, only liter. That means now the liter is cancelled and we have mole. So 10 to the power of -4 mole. This is the number of of protons in our solution. And now when we want to neutralize, how many hydroxide ions do we need to become a pH of 7? 10 negative 4. So we have to add exactly this number of moles of hydroxide ions. And we can do that step by step, drop-wise. And therefore, we draw a graph. We have the pH. And the added milliliter of sodium hydroxide. So here, the sodium hydroxide addition in milliliter, the concentration is the same as above mentioned. And the y-axis is the pH level we observe. And this is 2, 4, 6, 8, 10, 12, 14. Well, 14 is the max. And we have addition of milliliter of NaOH. 1, 2, 3, 4, 5, 6, 7, 8. So we add milliliter per milliliter of the NaOH. Already mentioned at the beginning, we start at the pH 2. What are you expecting when we add now NaOH? Will slightly increase. And what are you expecting when we had the same volume NaOH as we had at the beginning in HCl? Here we will have 7. So that is fixed. Here is 7 and here is 7 after 10 milliliters. So we will have 7. And when we had a huge amount of more NaOH, where will we end up? Yeah. What we can exactly say? We can exactly say where we will end up. Not 12, because the concentration is 10 to the power of -2, means the pOH is 2, the pH must be 12. So we will end at 15, 16 milliliter, whatever, at a pH level of 12, something like this. And the curve looks like that. It slightly increases. And then we have a dramatically increase nearby the neutral point. And then it starts to become alkaline. So it will look similar to this curve. Here we have the increase. It will look similar to that. And this is what we call the equivalence point. Not more than that, because we don't have more than 2 to the power of -2. If everything is neutralized, we end up at 12. The pH will be 2, but the pOH will be then 2 and the pH 12. The sum is always 14. The equivalence point is the point where it's neutral in this case. And in this case, we have, when we do it mathematically, the change of the pH at that point is highest ever. That means when the gradient is very high at that point, we can try to create this, how do we call it? Tangent, yeah? And this is the highest change at that point. At that point, the biggest change in pH level. Now, just to ask you, think about when we have now here this concentration of a strong acid, and now we don't add a strong alkali, we add a weak alkali like ammonia. Do you think we need more to neutralize, more volume in the same concentration, of course? Yes. We will end up at 10 to the power of -4 mole of these OH minus again, but we don't have them because it's a weak acid. It's not creating so many OH minus as the strong alkali. If we use a strong alkali and we titrate with an acid, it's vice versa. We start at the pH level which is high, and then we will drop. If we have a strong alkali and add a weak acid, yeah, we will need even more until the pH comes down again. And in nature, we have it even more difficult. Maybe you heard about a buffer. What is a buffer?
The buffer solution is tries to maintain the pH.
Yeah.
So for example, our blood is a buffer solution.
Yeah, very good. Our blood is a buffer solution, and this is good for us because when there is any kind of attack in our body, in your stomach, you have quite a lot of acid. If there's something leaking and coming to the blood, the buffer balances, the blood balances it. And so we have a buffer system in our blood which tries to keep stable the pH level in a special range. In chemistry, we have buffer systems for quite a lot of different pH levels. When we try to maintain a reaction, and the reaction is, for example, depending on the pH, if it is going well or not, we'd like to buffer the system that the pH doesn't change, that we always have the same conditions for our reaction.